Alright, so in this video, we want to go over some thermodynamics practice questions coming from this tutorial sheet. We've got questions 1 up to 5. So just a basic energy profile diagram, and then look at the first law of thermodynamics. On question 2, question 3, we'll look at the calculations that involves heat. Okay, and then 4, we'll look at calculations of enthalpy of the enthalpy using the enthalpies of formation, and do the same for 5, the enthalpy of the reaction when we're given the other reactions. So that is S's law. And then lastly, we'll look at question 6, where we go over the use of bond enthalpies in calculations of the enthalpy of the reaction. Okay, so let's start. Question 1, nitrogen gas reacts with the hydrogen gas to form ammonia gas, and 91.87 kilojoules of energy is released to the surroundings during this reaction. A says write the balanced chemical equation for the reaction. Placing the energy on the correct side of the equation, draw an energy profile diagram for the reaction indicating the reactants, activation energy, enthalpy change. According to your answer in B, the potential energy greater for the products or less than to the potential energy of the reactants? Give a reason for your answer. So we'll start over from question 1. Okay, so we have the reaction between nitrogen gas, and then nitrogen gas is reacting with hydrogen gas. They both exist atomically, so to form ammonia gas. So ammonia gas is NH3 to start with. Okay, all these are gases. You can add the states: gaseous, gases, 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 gases. Okay, now is the equation balanced? No, it's not. We have to balance. How do we balance? We've got 3 there for the hydrogen, so we can add the 3. That would now require us to put a 2 there so that we can balance the hydrogens. Okay, so that's now balanced. Now A is saying not only are we writing the balanced chemical equation, we should also indicate the energy, place it on the correct side of the equation. So what are we told in the question? We are told to say that amount of energy was released. So is this endothermic or exothermic? So it's an exothermic reaction. Okay, so there are 2 ways of presenting based on the way the question is asked. If we had it, it should appear when it's exothermic, it means energy is being produced, right? So which would make it a product. So we can add it on the right side of the equation, plus 91.8 kilojoules. This is more like a product. Okay, now there are other ways that we can actually indicate, as you would see from this question. If I put it at the end like that, it's different. In this case, I'm not adding it as either a reactant or a product, but the sign indicates whether it's exothermic or endothermic. The negatives are exo. So we've answered question 1, A. Question 2, question B, we have to draw the energy profile diagram for the reaction, correctly indicating the reactants and products, activation energy, and enthalpy change. So this is an exothermic reaction. Okay, so I'll remove this just so that we can have enough space. So energy diagrams, usually energy profile diagrams, are in 2 types. There's one which is like this, and then there's one like this. So one thing that you need to understand is this indicates the reactants, this indicates the products. So this is where, of course, on the right you're talking about the energy. Okay, so this implies this is reduction in energy, which is exothermic. This is endothermic, increase in energy. Okay, that's simple to understand, that's simple to see. Okay, so in this reaction, what kind of reaction do we have? Do we have an endothermic or exothermic reaction? So the reaction we have is exo, implying that the energy of the reactant is going to be higher than that of what? The product. Okay, so we'll start somewhere up like that. So this is now where we've got our reactants. What do we have as reactants? We've got nitrogen reacting with what? So we've got nitrogen reacting with our hydrogen. Okay, you can write it as it is balanced, indicate the states as well. I will not indicate the states, but you should indicate the states. These are our reactants. Now, for reaction to actually progress, there's need of what we call activation energy. Okay, there's need for what we call the activation energy. So that's now where you see the energy going up. This is going to be something like this. Okay, it usually makes sense if it's round. Okay, so this is an exothermic reaction, so it has to come down lower than the products, or rather than the reactants, so that we have our ammonia gas there. Okay, so I have to indicate that which one is our activation energy. Our activation energy is this part. So where you are seeing that is the activation energy. Okay, now the difference between the energy of the reactants and the products, this difference, this is now what we call the enthalpy. Okay, delta H. So the question said we should indicate the reactants, the products, the activation energy, and the enthalpy change. Okay, so I've indicated for us now. Okay, so I hope you can see the activation energy. Actually, the activation energy makes it's supposed to be something like this. Let me put it properly. From that point to this point, you look at the energy of the products, the reactants, sorry, up to what is required for the reaction to progress. That's activation energy. Now the energy difference between the reactants and the products is the enthalpy. Okay, I hope that makes sense. Now we can move. C says, according to your answer in B, is the potential energy of the products greater than, less than, or equal to? What do you think? So if you try to look at your reactants compared to product, you see that since on the left, this is where we have energy on the y-axis, that's a level of energy. Okay, this is called the energy profile diagram. This shows the progress of the reaction. Okay, so basically then you know what we're talking about. Okay, so that has got higher energy than this. So the reason is very simple. Potential energy of the products is less than that of the reactants because they were losing energy. The reactants were losing energy. Okay, so they are the greater energy because compared to the product. I hope that makes sense. Now on question 2. Question 2 is simple and straightforward. Here we are told the first law of thermodynamics states that the change in the internal energy of a system is equal to the sum of the heat gained or lost by the system and the work done by or on the system. So the summary of whatever we've read there is the internal energy, which is the change in internal energy, is equal to the summation of the heat, okay, plus work. Okay, so this is it. It can either be positive or negative. It is positive when it is gained. It is negative when it is lost. Then the other part is work. It can be positive or negative. Work is positive when it's done on the system. It is negative when work is being done by the system. Okay, that is very simple for us to understand. Now applying that concept, we should be able to answer all these questions A, B, and C. So A says a gas absorbs So don't forget about our formula. So for air, a gas absorbs actually 45 kilojoules. So is that gain or loss of it? Absorbs. So that's gain. Okay. So 45, and then does that amount of work. So a gas is doing work. So it's work done by what? By the system. So it's a minus. Okay. Calculate the change in internal energy. So you just subtract the two. You get 16 kilojoules. Okay. I didn't include the units because they are both in kilojoules. Okay. Pay attention to that. Now if you go to B, pause the video and just try it out. B says a system releases. So that is emission, that is loss. So what do you think? So it will be negative 125 kilojoules, while 104 of work is done on it. So done on this work is done on the system. That will be a positive 104. So therefore a change in internal energy will be the difference. Negative 125 plus 104, negative 1 kilojoules. And then finally C, what do you see there? Step 1, the system absorbs 72. So absorbing is what? Gain. So that would be 71 of it energy. And then while 35 joules of the work is done on it. So absorbing is positive, work done on it is also positive. Okay. And then for step 2, the system absorbs. Again, that is positive while performing. So doing work is energy is lost. So that is minus 72. So in short, for change in internal energy, for the 2 steps in summary, step 1 has its own answer there, step 2 has its own answer, and then you get to add them. Okay. So 71 plus 55 for the first one gives us 106, plus the other one, which is 35 minus 72, gives us minus 37. Okay. So 106 minus 37, that gives us what? So I don't know my calculations. This is giving me 69. Okay, joules. Okay, so if our computations are all fine, then that's what we have. Okay, 71 plus 35 is 106, right? And then 35 minus 72. So this is what we have for question 2. Question 3. Suppose you pick up a 16-gram ball of iron, such as a shot put ball, at a track event. Now the iron ball has the same temperature as the atmosphere on a cool day, 16 degrees Celsius. Calculate the amount of heat energy that the iron ball must absorb to reach a temperature of your body, 37 degrees Celsius. Suppose you pick up a 16 grams ball of iron. So take note of the data there. So 16 grams of ball of iron. Okay. You are picking up that. Okay. And then the iron ball, we are told the specific heat capacity is 0.451 joules per gram degrees Celsius. As the same temperature as the atmosphere on a cool day. So the temperature of that iron ball is that of the atmosphere, which is 16 degrees Celsius. Now calculate the amount of heat energy that the iron ball must absorb to reach the temperature of the body. So this lies in the fact that if two things are to be in contact, they are supposed to head to a place where the temperature becomes the same. Okay, so if you combine even water, right? This applies even to liquids as well. If you get water at 40 degrees Celsius, you combine it with water at 75 degrees Celsius, the final temperature is going to be in between. Okay, so they want to reach an equilibrium temperature. So even you, when you get to hold the iron ball, you pick it up, your body temperature is 37 degrees Celsius. The initial temperature of the iron ball is 16 degrees Celsius. So the final temperature should be what? Should be in the middle. Okay, so for that to happen, energy is supposed to be lost from the high temperature, which is 37, to the lower one. Okay, so that's why they are saying calculate the amount of heat energy that the iron ball must absorb. So the formula that you should always think of when you see such questions, think of MCAT. M, specific capacity change in the temperature. Okay, so our Q, which represents the heat energy, is going to be, our M is what? Our M is the mass, 16 grams of the iron ball. Specific heat capacity is 0.451 joules per gram degree Celsius. And then multiply by the change in temperature. The final one, what is the final one? This is now where you have to be okay. Calculate the amount of heat energy that the iron ball must absorb to reach the temperature of your body, 37 degrees Celsius. Okay, so what must happen? That means that its final one is 37. Then the initial should be what? 16. This is degrees Celsius. So degrees Celsius will actually divide. The grams will equally divide. So we just remain with the joules there. Okay, so our Q therefore becomes 16 multiplied by 0.451 times 37 minus 16. That should be able to give us the energy that must be absorbed in this case. So what I'm getting 151.4 joules. This is the amount of energy that the iron ball must gain or must absorb for it to reach to that temperature of your body. This is only because, why is it so? This is because the temperature of the body shouldn't change, right? So it's constant, so the iron ball has to adjust. Now if you go look at B, it's a similar question. A sample of platinum metal weighing 18.7 grams experiences a temperature rise of 2.30 degrees Celsius when 5.70 joules of heat is applied. What is the specific heat capacity of platinum? So we've got platinum metal, which is weighing 18.7 grams. It experiences a temperature rise of, so when you see a rise or a change, just know that that's representing the delta T. Okay, and then when 5 points, so this is energy, right? So that's your Q. When 5.70 joules of heat is applied, what is the specific heat capacity? So you can actually see that if you look at the formula MCAT, you take this to be your S so that you're able to remember the formula easily. Okay, so if you try to make specific heat capacity as a subject of the formula, you have to divide by M and delta T. Okay, so our specific capacity, our energy, heat energy is 5.70 joules. Our mass is 8.7 grams. Our change in temperature was 2.3 degrees Celsius. Okay, and then that is on top, that is in joules. Okay, so 5.70 divided by a product of 18.7 times 2.30, that should give us our specific capacity. So I'm getting 0.131 joules on top per gram multiplied by degrees Celsius. Okay, so what is the specific heat capacity of platinum? Okay, so we're on question 4 now. Question 4, we are told calculate the enthalpy of the following reaction. Okay, so if you're enjoying this video, I just wanted to let you know to say I've actually taught this topic from scratch, from defining what thermodynamics is or thermochemistry is, moving on to the change in internal energy, the laws of thermodynamics and whatnot, moving on to the questions that we are from looking at, okay, looking at the calorimeter questions as well, and then moving on to enthalpy calculations, S's law, and many other concepts under this topic. In full, with several other videos that you can actually watch with several practice questions to solidify your understanding of this topic. On that site you find all the other topics in chemistry, and of course the full solutions to this video, because this is gonna be the last part of the video. Okay, so let me give you the formula. Actually, there's a PDF accompanying our solutions. There's a PDF accompanying these solutions that we've done in this video. There's a PDF on our site. The link is in the description below. Okay, so when you are taught to calculate the enthalpy of the reaction, when they've given you the enthalpy of formations, you basically, what helps me remember the formula for that is what are formed, the products, right? So the change of the enthalpy is given as the summation of the energy of formations for the product minus that of what? Their reactants. Okay. Now, one thing that you have to know is these ones that are existing in nature, they don't have enthalpy of formation. Their values are zeros. That's why if you look at the given values, we don't have any value for oxygen, because the oxygen exists naturally. Okay, so let's calculate. How do we go about it? So to calculate the enthalpy of formation for the products, we've got carbon dioxide and water. So the values we've been given are per moles. Okay, so carbon dioxide, we only have a single mole of carbon dioxide. So if you check CH4 methane, it's 74.8. For carbon dioxide, it's that. And then finally, this is for water. So for carbon dioxide, we only have a single carbon dioxide more, plus we've got 2 water molecules. So these are representing the values for the enthalpy of formation of the products. Those of the reactants, we have methane and 2 oxygen moles. So it now substitute carbon dioxide. What's the value for carbon dioxide? It's negative 393.5. Okay, based on what the question is saying. And then water, since water was the last one to be listed, you go for the last value. That's negative 286. Now look, pay attention to what I've done here. Specifically what I've done is I've put multiply by 2, right? I've put multiply by 2 because there are 2 water molecules in the in the balanced equation, minus methane. The value is what? It's a first value there, negative 74.8. It's just a single mole. For oxygen, it exists naturally and the value hasn't been given, so it's just a 0. Even if multiplied by 2, it will still be a 0. Okay, so how do we calculate now? So just add what's in the brackets there. Okay, so I'm getting negative 393.5 minus 572, and I multiply by 2, and then in the other bracket we're just having minus negative 74.8 still stands, and then negative 65.5 when you subtract these, and then the sign there becomes positive, so plus 74.8. now which will give you a final answer of what? Negative 890.7. This is kilojoules. So what is the enthalpy of that reaction using the enthalpy of formations? Okay, so to access the full solutions to this video and the PDF solutions, please use the link in the description below. And of course, when you do access those, you're also going to learn the topics in full. Actually, each question here has got like each own lesson with its own more practice questions on our site. So use the link in the description below, learn.transcendedinstitute.net, and you'll be able to access chemistry as a full course. Okay.